The previous lesson on parametric equations looked at a different way to do equations and graphs. Now we're going to look at a totally different way to do points. So all the time you've been looking at points, you've been looking at x and y. Those are going to be called rectangular coordinates, which you've been used to. And they work on a rectangular, on a square grid. You look at how far you go sideways, and you look at how far you go up and down. That works great when things are rectangular. But a lot of things in life are round. For example, the Earth. Hopefully, we don't have any flat earthers out there, but the Earth is round. And so often for mapping the Earth, we look at this, what's going to be called a polar coordinate system, where we look at a round way of mapping space, of finding locations. If we look at the way the planets move, the planets rotate around. So for planetary motion, this polar coordinate system works out really well. If you've ever seen the radar screens where there's a circle and there's kind of a line going around and the kind of blips of location there, that works on a polar coordinate system. Microphones, picking up sound in a microphone, works in a circular fashion. Now, there's all kinds of applications where you want to find locations based on a round system, not a rectangular system. And so that's what polar coordinates do for us. Polar coordinates, we're going to look at an r, which is a distance from the origin, and we're going to look at a theta, an amount that we've rotated. And so if you wanted a polar graph paper, it would look like this. They would have different concentric circles for different distances from the origin, and then they would have marked some of the common angles, and you could find locations like that. So for example, this one right here, if we had 2 comma pi over 3, it's alphabetical. Theta is the Greek letter T. You actually want to look at the angle first. So we would look at the angle pi over 3, and then we would find a distance of 2. Looks like they're saying that's this circle here. And so we would have this point right here. Now for us, though, we're really just going to try to find the approximate location. As long as you know what quadrant it's in, really usually you're going to be fine. And so we would say an angle of pi over 3 is somewhere around here, distance of 2, just kind of approximately. As long as you can get it in the right quadrant, we'll be happy. And so this represents this point right here. If you're plotting the point, all you would have would be that dot right there. But kind of behind the scenes, what's going on is that you've rotated pi over 3 right there, and then you've gone a distance of 2 from the origin. Now, it might seem a little bit strange, so you're used to distance being positive, but we actually allow r to be negative. And what happens when r is negative is that you go to the opposite quadrant across the origin. So for this one right here, 3 pi over 4, we know is in the second quadrant. So here's 3 pi over 4, this rotation. But then because the r is negative, because we have that -1 right there, the point is not going to be in the second quadrant anymore. That negative r flips us across the origin into a different quadrant right here. So instead of being in quadrant 2, we're going to be in quadrant 4, a distance of 1 from the origin. If you have a negative angle, that's not going to be anything special. That'll work just like normal. Negative pi over 2, we just rotate backwards, and then we go a distance of 3 from the origin. So we would be straight down, a distance of 3. It's just these negative r's that are special when you're in the opposite quadrant. Okay? Now, one thing that's interesting about polar coordinates is they're not unique. So if you look at a point in space, there's only one x and y to get there. You have to go this distance sideways and this distance vertically. There's no multiple options for an xy for rectangular coordinates. But for polar coordinates, actually there's an infinite number of different polar coordinates for the same point. The easiest thing is to look at the angle. We know that there's multiple angles that land in the same spot. We had a word for that. And so if we look at this point right here, 2 comma 2 pi over 3, 2 pi over 3, and then this -4 pi over 3 land in the same spot. And so if I keep the r, the distance from the origin, the same, and have 2 angles that land in the same place, then the point is going to be the same. The word for that again was coterminal angle. So any coterminal angle with the same r will give you the exact same point. All right, so that's one option here. Now we don't have any other coterminal angles here though. So how are we going to get two polar points? How are we going to get another one? Well, the other way that you could do it is that you could use a negative r. So 2 comma 2 pi over 3 was right here. That's this point that we want right here. Well, I could also get this point by using a negative r. And if r was negative, then I would want my angle to be in the opposite quadrant. I would want a fourth quadrant angle and then a negative r to flip the point back into the second quadrant. I have a fourth quadrant angle, negative r. The point will be back here in the second quadrant. So if I'm looking here for a fourth quadrant angle, that's my 5 pi over 3. Can't just use positive 2 anymore, though, because positive 2, 5 pi over 3, that would be a fourth quadrant point. I want this negative r here. That negative 2 flips it back so that it matches that point right there. And then they are equivalent. All right, so another thing that we'll want to do is to be able to convert back and forth between rectangular. Again, rectangular is just x and y. Rectangular is always just going to be what you've been used to. And so, of course, we've got lots of relationships here. If we draw this out, we've got the same picture that we've seen over and over and over again in this class here. If r is the distance from the origin, the hypotenuse, if we've got our theta in here, the y is the opposite side, the x is the adjacent. And so all of these trigonometric relationships are still true for sine, cosine, and tangent. We've also got the Pythagorean theorem. Again, what we did with the sine and cosine relationships, we start with cosine theta is x over r, and then we just multiply both sides by r, and that gives us this equation right here. And do the same thing for sine. These should look fairly familiar to you. Those are almost exactly the same as what we had for vectors. Vectors were almost exactly the same thing. Just instead of calling the distance along the hypotenuse the r, we called it the magnitude. But we still had an angle, we still had an x and a y. So we've got almost exactly the same relationships. Instead of x is the magnitude times cosine, we've got x is r times cosine. Instead of y being the magnitude times sine, y is r times sine. It's all the same exact relationships. One slight difference, though, is that r is allowed to be negative. R can be positive or negative. So we leave the Pythagorean theorem equation as just x squared plus y squared is r squared. For vectors, we had the equation square rooted already because magnitude was always positive. And so we could say magnitude was just the square root. Here we leave it with the squared because then when we square root both sides, we'll get that plus or minus. But it's all the same for relationships. So I've put these in this box right here because they're really, really important. You really want to make sure that you're familiar with these four equations. That's going to be your keys to solving a lot of these problems right here. Okay, so converting to rectangular is going to be pretty easy. So if we're going to rectangular, that means we're starting out as polar. If we're starting out as polar, that means that this is the r, and that's the theta. And rectangular is the x and the y. So we want x and y, and we know r and theta. Well, that's going to be these equations right here. These tell you what x is when you know r and theta, and what y is when you know r and theta. So we can just say x is 2 times cosine of pi. And cosine of pi, pi is on the straight to the left, has an x-coordinate of -1. So that's the cosine. 2 times -1 is -2. And then the y, just like on the unit circle, x goes with cosine, y goes with sine. And sine of pi is going to be 0. So that'll be 2 times 0 is 0. And so our point is -2, 0. Finding rectangular is super easy. You can just kind of plug and chug into those formulas right there. Now, some of them might be a little bit easier. This one you could have kind of figured it out on your own probably. If you take a look at this, an angle of pi is straight to the left, so we went straight to the left a distance of 2. Well, I think most of us know straight to the left a distance of 2. That's the point -2, 0 in rectangular. So sometimes you could draw them out if you want, but the formulas work very nicely. All right, now going backwards, notice we have some kind of more complicated directions. We can't just say convert, because again, there's that issue of there's an infinite number of polar points for any place in any location in space. And so we're just going to ask you find one. Just give us any polar point. But to try to narrow it down a little bit, we'll restrict you to using angles that are between 0 and 2 pi. So notice we do want radians. All right? And so now we know the x and the y. This is a rectangular point, and we're trying to find the polar point. So we're trying to find the r and the theta. So if we know x and y, we want r and theta. That's going to be the bottom two equations right there. So I'll start with this one here. I'll say -1 squared plus 1 squared is r squared. So that's going to give me 2 equals r squared. So r equals plus or minus √2. We're going to have to pay attention to that. Remember, when you square both sides, you get plus or minus. R could be either positive or negative. We're going to have to think about that. And then to find our angle, I mean, at this point, you know r, so you could use cosine or sine if you wanted to, but it's always safer to use the given information. So that's why we typically use tangent to find our angle. So we're going to say tangent of theta is y over x, 1 over -1. So we want our tangent to be -1. Well, for tangent to be 1, we need the y and the x to be the same. We should be thinking our pi over 4 angles. We want some sort of pi over 4 angle, but we want tangent to be negative. So again, in this class, ASTC is probably the most common thing that you should be doing over and over and over again. Tangent being negative, that's second and fourth quadrants. So a second quadrant, pi over 4, that's your 3 pi over 4. And fourth quadrant, that's your 7 pi over 4. So we've got 2 different angles that are options, and we've got 2 options for r. So we just need to find one pair that works. So here's the key. Go back to your original point. Figure out where it was. -1, 1. We can all plot that point. X is -1, y is 1. That's in the second quadrant. This is absolutely the key. Because for a lot of the stuff in chapter 6, you want to take a look at what you're starting with and what you're ending with. Make sure that they're in the same place. So this point was in the second quadrant. So that means that 3 pi over 4 angle makes a little bit more sense. So that's the one that's going to get the positive r. If the point and the angle are in the same place, use a positive r. This is the answer that might make a little bit more sense. And we only asked for one, so if you want to just give us that answer and be good, then you're good to go. The other option that we would accept here, again, you don't have to give us both, you only have to give us one, but the other option is using this 7 pi over 4. Now that one might seem a little bit trickier. If the point is in the second quadrant, then how are we going to use a fourth quadrant angle? If the angle is in the fourth quadrant, then how can the point be in the second quadrant? Well, that's what the negative r does, right? A negative r flips it from the fourth quadrant back to the second quadrant. It gets you in the opposite quadrant right there. So now we've got another option, but again, either one is fine. So one more problem here. Again, we're starting with rectangular, so this is x and y. So I'm going to say x squared, which is 4, plus y squared, which is 9, equals r squared. So that tells me that 13 is r squared, which means r is plus or minus √13. Okay, don't forget that plus or minus. We're going to have to think through whether we want r to be positive or negative. So then for my angle, I use tangent. Tangent of theta is y over x. Now that is not something on our unit circle. We've got square root of 3's on our unit circle, but not just 3. There's no way to make that be like something on our unit circle. So this one would be a calculator problem. So we're going to use inverse tangent of 3/2. And we'll make sure that we're in radian mode here because of those directions right there. So inverse tangent of 3/2. And so I get 0.983 for my angle. I'm going to have to figure out, though, does that go with the positive r or the negative r? Always look back at your original point, -2, -3. That's in the third quadrant. All right. Well, it was a little bit easier to tell the quadrants back here. Do we remember how to figure out quadrants when it's a decimal, I wonder? Well, let's take a look here. We're trying to figure out 0.983. Well, what we did was we said we know pi is over here, and pi is about 3. 3.14 goes on forever. About 3 is usually enough. So then pi over 2, half of pi, was about 1.5. So that means that the angle that I've got here, this angle there, is less than 1.5. So it's in the first quadrant. Well, would a first quadrant angle work with a third quadrant point? It actually would. We just need a negative r. That's what the negative r is going to do for us. It's going to flip that first quadrant point over into the opposite quadrant, the third quadrant. So I can use this angle that my calculator gave me. I just need to pair it with that negative r. Negative root 13 with 0.983. And we only asked you for one polar point, so that's really all you need. If you did want to think about the other option, or if you were thinking, hey, this is the third quadrant point, I need to find the third quadrant angle, the other option would be to think about, okay, if I want a third quadrant angle, if I want to find that, well, what I found was the reference angle here. That 0.983 would be in there as the reference angle. And so to find your angle, you would do pi plus 0.983. Go on your calculator, add pi to that, and get about 4.124. So that would be the third quadrant option. And so if you had a third quadrant angle, that would be where you could use the square root of 13 positive. So either point would be perfectly fine. You only have to give us one.